Hello and welcome to the Path to Plutus channel. The goal of this channel is to help you along your path to becoming a decentralized applications engineer through learning a powerful functional programming language called Haskell and then a subset of Haskell called Plutus, which will allow you to build native smart contracts on the Cardano blockchain should you so wish. This is the first video in a series of videos that will allow you to firstly pick up Haskell itself. We'll go through the basics and will hopefully make you really experienced by the end. I just will introduce myself before I continue through this onto this video. My name is Vincent Almeida and I am a software engineer by day and have a computer science degree, having studied a blockchain-based dissertation. If you haven't already seen the introduction video to this channel, do head over to the channel and take a look at the video. I do appreciate that it's a bit of an investment in terms of your time at 45 minutes, but I promise you there's some valuable information in there as to why I'm doing these videos, why functional programming is important, especially in the blockchain space, and keeping people's money safe. So do head over and check out that video if you can, like it, subscribe to the channel, share that video. I think it'd be great for as many people to see that as possible. And if you can't spare the time to view the entire video, what I do recommend is you at least watching maybe the last 5-10 minutes of the video, because that actually includes instructions on how to set up your local computer to allow you to code in Haskell. So it'll go through how to install the Haskell platform on Unix-based machines such as Linux and Mac OS, as well as how to install Haskell platform on Windows. There's a bit more configuration that you need to do, but it's really easy to set up. And once you're going, you should be able to access your either terminal if you're on a Unix-based machine or your command prompt, and you should be able to fire up what's called an interactive command prompt that interprets Haskell code on the fly. So just before I continue, there's going to be two types of people watching this video. The kind that previously have programming experience like myself, who maybe do it on a day-to-day or have learned it in their own time. Those people will find this potentially a lower barrier to entry, but I'm going to try and aim it at as many people as possible, so that, provided you have the grit and determination to pick up this programming language, you hopefully have a good shot. If I need to, I'll make a separate video series that bridges the gaps between what beginners might not know and a particular concept I'm trying to teach in any particular video. So hopefully, people at least have a shot regardless of whether or not they've done programming before. The series of videos on Haskell are going to be based on the book, Learn You a Haskell for Great Good. Have a little Google. The book is free to read online. I found that it's made learning Haskell an enjoyable experience. And if you were thinking of buying a paper copy of this book, I couldn't recommend it enough, to be honest with you. A lot of programming books, if you may be able to relate to this if you've ever read a book on learning a programming language, a lot of programming books can be a bit of a dry read, and this one puts a fun spin on it. But what it does that I'm going to try and do differently to the book is I'm going to try and put a blockchain cryptocurrency theme on the examples and what I teach, just to make it a bit more interesting, and also because this is the path that will lead you to learning Plutus and build Cardano native smart contracts should you so wish. So taking a completely different angle on Haskell really, and showing you how if you wanted to, you could use it for not just building standard desktop applications. You could build desktop or server applications. You could pretty much build anything you want, but you could also build smart contracts with Plutus. So that should be really fun. in the channel's introduction video, I go into things like why functional programming, is important, what it means really. So I just want to build on that to kick off this video and talk about the fact that Haskell as a programming language is fairly lazy. And so what that means is, say for example, you have a list of 4 numbers, 1, 2, 3, and 4. So you had this list and you wanted to double every single item in this list. So you wanted to double the number 1, you wanted to double the number 2, etc., for every item in this list. So you would come back and you would get, 2, 4. Yeah, so you would get that. And say you wanted to do that a number of times. Say you wanted to take the output of the last operation and provide it as an input into the same function, which will perform the same operation multiple times. In a procedural language such as Java, C, C++, you would have to loop through the list every single time, come back, produce new output, etc. And if you had a really long list, this could end up being a really slow, monotonous process. And what Haskell does by being lazy is it goes through each item in the list. So for example, in the original list, 1, 2, 3, 4, it would go through each item in the list starting at 1, and it would pipe the inputs into each function rather than going through the list every single time. So basically it will start off with 1 and pipe that into the function that's going to be doubling it, so that you get 2, and then it will pipe it through the next one that you've chained along, and then it'll get 4, then you get 8, and so on and so forth. And you can therefore chain a number of these operations together in an infinite manner, and the list will only get traversed once. Now, that is a very, very powerful concept and is applied to many different aspects of the Haskell programming language. Basically, all you need to know is that a computation only takes place when the code wants to display the result to a user. So only when we want to display the result of doubling a number to a user does the doubling take place. So I hope that makes sense. The other thing about Haskell is it is a statically typed language, which is different to something like PHP. So basically, at any point in time, the Haskell compiler knows what every bit of code in Haskell is. So for those unfamiliar with compilers just translate the code that I would write, you would write, into something that the machine can understand, i.e. ones and zeros. Now that during that compilation process, Haskell will know that if we say that a is equal to 5, it will know that a itself is a number. So this is a number when you come and reference it later on. And what that does is basically it means that you can build functions like a double, let's say it's called double number function, where you supply a number as an input. It knows that that function can only take a number and not anything else, not a string, a sequence of characters. Anything other than a number is just meaningless, really. And that's very different to a language like JavaScript, where functions have to put guards in place to check what's coming in. Before it does a computation, it needs to make sure that if it's going to do a computation with numbers, it needs to make sure that everything that's been supplied to it, all the information supplied to it, are numbers. And you have to do that check manually. If you're a considerate, careful programmer, you will do those checks. It's easy to forget to do those checks, and it can make for very unstable code. So that's why linking, going on from what was said in the channel introduction video, functional programming allows somebody to more easily reason about the behavior of a program. You know, what it's going to do at any point in time is much more predictable than a procedural, you know, or object-oriented application will do. And you know, that can increase the security, it can increase the robustness of your application. And the other thing is, Haskell is a very concise programming language. When you write Haskell and you compare it to the equivalent that you would maybe write in Java or C#, the resulting code is a lot more concise in Haskell than it will be in Java. Especially Java is a very verbose language, and you'll appreciate that if you've ever written in Java. You know, especially when you're doing things like defining a static variables or member variables against classes. You have to write a public static final, or when you write, yeah, that will be if you're doing constants, string, blah is equal to blah, and you know, it's little things like that end up making your code very verbose. Now, there is a language developed by JetBrains, who produced the IntelliJ IDE, the integrated development environment. And they built a language called Kotlin, and Kotlin is a lot more a more concise version of Java, and I'd say Haskell is even more concise than that. So yeah, it's been fun learning it, and it would be great to share this with you guys. You know, hopefully in the future, what I can do is build maybe a smart contract on the Cardano blockchain that will, that when given the answer to an exercise that I've made up, if it's the right answer, will issue you with a badge saying lesson 1 completed. You know, you got the right answer. So I think that'll be a nice thing to do and to aim for. Probably, you know, do some videos on the channel and show how that's done. And I think that'll be a fun way to learn how to build some smart contracts amongst, you know, there's other things. There's many ideas for building smart contracts. You can build your own lottery, a transparent lottery, etc., etc. So let's get stuck in and dive into learning the basics of Haskell. So at your terminal or command prompt, fire up the interactive prompt. Now, if you come from the world of Python, Python has this interactive prompt where you know, code can be interpreted on the fly. You can, you know, perform calculations, run functions. You know, you can run code basically line by line. Now, the compiler that I was talking about earlier for Haskell is called the Glasgow Haskell compiler. The acronym obviously for that is the GHC, and to get the interactive shell, you need to type GHCI, and that will fire up the interactive prompt. And you'll know that it's launched successfully with this prelude message. Really simple, hopefully, so far. So if you've got prelude, you're on the right path. So like I said, you can do some calculations, you know, 4 plus 4. So you can do addition, subtraction, division. Now with division, the forward slash produces what's called, if you're not familiar with it, it's a floating point result, which just means it's got a decimal. And you can do division on integers only, and it will produce an integer result. But that's a different method, and I will get round to showing you that in a bit. But I don't want to complicate things too much to start with. So yeah, so that should be, oh, don't do that. Doesn't recognize that character because basically the mathematical operators require numbers for both inputs. You know, so if you supply anything else, it's just not going to know what to do. You know, and you can't do things like 5 times the character 5. It's just not going to know what to do really. But what you can do is obviously, you know, 5 times 5, you get 25. You can do powers, so 5 to the power 2, yeah. So that is good. Now, I just want to talk to you guys a little bit about precedence, and especially, if you've never come across this concept before in a programming language, and it just means that there's an order to which mathematical operations will take place. So, for example, if we do 5 times 2 plus 1, multiplication has the highest precedence. It means it will get executed first, right? So what's going to happen here is the mathematical equation 5 times 2 is going to be executed, or expression, it's called in programming languages, and then 1's going to be added to that, so we will get 11. But if we wanted to do 5 times 3, if our actual intention was to do this, we would so add 1 to the number 2 first, and then multiply by 5. We should get 15 here, and indeed we do. Now the reason that is because parentheses have the highest precedence. So just by wrapping something in brackets, in parentheses, you get the highest precedence possible. So that thing will be done first above everything else. So right now, as you think of it, parentheses is the highest precedence, then multiplication, division, subtraction, addition. I think it is, or it's addition, subtraction. I can't remember which way around it is, but the ones that cause the problem mostly is going to be multiplication and division. And whenever you're not sure, or anything seems ambiguous and you want to guarantee the order in which something is executed, just wrap things in parentheses. There is something that is below parentheses, and that is function calls. So, but we'll get into that in a bit. Haskell deals with negative numbers in a weird way. So you saw earlier you could do subtraction. So that the result of that is 4. But say for example you had you were keeping track of the temperature of 2 cities, and one city was 67, and you wanted to find out what the sum of the 2 cities were. I mean, that could be Fahrenheit. But another city was Fahrenheit, Celsius, it doesn't really matter, but basically this is not going to work. So it's going to throw a hissy fit because it thinks that you're getting confused and you don't know whether you want to add or subtract. It's trying to treat these 2 things as isolated things, so the addition taking place and a subtraction. So this plus is expecting 2 numbers on either side of it. It's expecting there's a 67 on the left and another number on the right, which in this case is 12, and that works absolutely fine. Now, the mathematical operations you see here are actually functions that simply take 2 inputs and produce an output. So 67 and 12, you can use this function like this as well. So you can say, I want to do addition, and the first number I want to do addition on is 67, the second is 12. And that does not work. Of course, it's going to show me up, but you'll see what I mean in a bit. But basically, by doing the operations this way, you end up using what's called an infix function, and this is naturally infixed, which is why it probably didn't work when I put it at the front. But if you remember, I said you can do division on 2 integers, and the result will be an integer. So the way you do that is you call the div function, and you supply 2 values. So I want to divide 5, and by itself 5, which should result in the integer 1. Okay, so that does result in 1, but you could also call this in an infix manner, which means to say, which is the opposite, obviously. So the first way we called div is in a prefix manner, pre to these 2 numbers, but you can also call it infix, which is where you sandwich between 2 things, and you can only do this for functions that have two inputs. So you still get 1. The backticks are there to say that this function is normally prefix. It's normally this. But what we're going to do is we're going to sandwich it in between something because it's more readable. 5 div 5. That's a lot more readable than what you previously saw. So yes, that's a bit about prefix and infix functions. Most functions are prefix. So there's a function called succ, S-U-C-C, and produces the successor of a number, i.e. the next number along. So that will produce the number 8. It's like doing 7++ if you're used to Java, C, C++, stuff like that. So that can come in, very useful depending on the calculations that you're performing. Okay, so the next thing I wanted to go on to is Boolean Algebra. So Boolean values can either be true or false. And notice that in Haskell, the true or false values have start with a capital. So it's capital T, capital F, true or false. And you can do algebra with these values. So you can say, what's the result of true and true? You get true, true and false, because both are not true. In a chain of Boolean values, if one of the values is false, doesn't matter if the other values are true, it'll always be false. And if you want to flip the value of a Boolean value, what you do is you use the not function, and it will return the opposite of the Boolean value you have. So it will return false for the starting value of true, and for the starting value of false, it will return the value of true. Quite simple and straightforward. Now with Boolean logic, numbers, you can do equality checks on these values. So you can do 4 is you can ask the question, is 4 equal to 4? And the answer is, in this case, yes. Equal to 5? No, it's not. If you want to do a not equal to check in some languages, that will be exclamation mark equals, not equals, but in Haskell it's / equals to do the not equals to check, and 4 is not equal to 5, so that returns true. You can also do it for strings, i.e. collections of characters. So hello is equal to the string hello Plutus devs. So you can compare a collection of characters. So character H is equal to H, E is equal, and you get the gist. Strings are quite interesting, and we'll be going into why that is later when probably in the next video. I'm not quite sure yet, but when we talk about lists, really, yeah, it probably makes more sense to talk about it there. But basically, a string is a list of characters, which makes sense, really. Okay. So the equality, so you could do, greater than, is 5, greater than 4, yes it is. You could have less than, you have greater than or equal to, etc. So, really straightforward. The only thing to remember versus other languages is that is not equal to, and it's rather than exclamation equals. But just remember, / equals is not equal to the not equal to check. So let's see if we can make our first function. So something that takes an input and produces an output. And what we'll do is, obviously, it will be a prefix function. Most functions are prefix, i.e. you type their name at the start and then supply some inputs afterwards. And the inputs are separated by spaces, which is quite nice and simple. It seems weird if you have previously programmed in other languages. It's a bit different, but you used to it very quickly, and it makes typing the code very quick. So yeah, for example, when I showed you guys earlier the suck function, so this is the function here on the left that we're calling. To get the successor of a number we supply, we separate the input by a space and we supply the input, which is a number. It takes only one input argument. So we only do one space and supply the number that it is looking for, and it will produce the successor to that number. Okay, and above multiplication, function application has the highest precedence, as I mentioned earlier, and then above that is parentheses. So everything will be done in parentheses before you get to a function call. So that's really important to note. So obviously, going back to the successor function, if we do the successor of 8 and plus 1, what we'll do is we'll get the result of 9, and we'll add to that 1 and you'll get 10. But if you wanted to get the successor of, right, yeah, so you'll get the same outcome here, but say for example instead of adding, we multiplied. So here you'll get the successor of 8, which is 9, and then it will be multiplied by 2, which will be 18. But if we did the multiplication first by surrounding it in parentheses, 8 times 2, you get 16. The successor will be 17. So you can see how precedence is very important if you are not familiar with it. Okay, so let's define our first function. So in the GHCI prompt, what you do to define your function is you just start by defining a name for that function. What label are you going to give to it? And then you supply the names for inputs you'd like, and that could be an unlimited number of inputs. You wouldn't really want an unlimited number. You would want, a handful of inputs. If you need a lot of, don't do that basically. But yeah, you'll have the label, and then you will have a space after the label. You'll define the first input, add another space if you want another input, and so on and so forth. So what we're going to do is we're going to define a function which takes the number of adder that an individual might own. So adder is the native unit of account for the Cardano blockchain, so named after Ada Lovelace. So it's a native token of the Cardano blockchain, and what we'll do is we'll write a function that takes the number of Ada somebody owns and returns how much it's worth in US dollars, and we're going to pick an arbitrary number for how much each token is worth, and then the end result will be that we can use this function to, given any number of adder, we will be able to establish the US dollar amount. Not that it's important, but it's a really easy function to make to start with. Okay, so what we'll do is we'll assume a token price of 8 cents, and we'll get started by writing our function. Now, when you give a label to a function, it cannot start with an uppercase letter, so you cannot do this. So currency tickers are normally all uppercase, like the US, the US dollar is normally USD. So you cannot give a function the following labels. So adder to USD. This is camel case notation. You can't do that. Because the first letter is an uppercase. So we have to instead start with giving the label all lowercase letters for adder, and then we'll use camel case for the rest. So adder to USD. So that will be the label of our function, and then I'm going to add a space to start the label for the input that we're going to be given. So the input that we will be given is adder, so the number of adder somebody might own, And that's all we need. We just need, because we were going to assume a price of adder, which will be 8 cents in this case. We don't need to ask them for the price of adder. At the end of the day, it wouldn't really make much sense to have a function that tells you how much. Well, I mean, I guess you could have a function which tells you how much your adder is worth if you knew both how much adder you had and what the token price is. But for now, we're just going to make this simple and say we're going to have a function which takes the adder, assumes a price of 8 cents per adder, and then we'll produce the result for you. Okay, so we have the label. We've added a space to add a label for the input, the name for the input, i.e. the argument that's going to be supplied. And then we're going to say equals, which starts the function and starts the part which actually will execute code, and this is going to be executing some very basic code. Okay, so all we're going to do is multiply number of adder supplied, and we are going to multiply it by 8 cents. That's all we're going to do. So to recap, we started by giving this function a label, adder to USD. It's simple and explanatory. You're converting adder to US dollars. We then added a space to specify that we're going to accept a single input. So that will be the number of adder, 1 ohms. And we've given it a label of adder. And then we've started the definition of the function, which will make use of this input on the left. So it takes this input, adder, and multiplies it by 0.08, 8 cents per unit of adder. Okay, we hit enter. We didn't get an error. That's good. So the Haskell compiler is happy with my definition of this function. So now we can try and use it. So if we do adder to USD, and we supplied, we say, okay, 575. How much is 575 adder worth at 8 cents per adder? Right? It's worth 46 apparently. Notice the floating points come back because we've done multiplication with a floating point here on the right, and that makes the result floating point. Even though we supplied an integer, we get a result of a floating point number. Now the reason that is because integers like this number here, 575, can behave like floating point numbers. There's some under the hood magic that leads to that, but it basically means that without much fuss, that integer can then just convert itself to a floating point number, and then we can multiply it by 0.08, apologies, and you get the answer of 46. So you get the gist of how this works. And we could define a function the other way around, so we could define a USD to add a function, and we would ask for how much USD, and you would get an answer out of that. So if you wanted to challenge yourself to figure that out, you could definitely go ahead and do that. So just remember, when defining functions, don't start with an uppercase letter. The other letters after that can be uppercase. We could have done adder to USD, but that looks a bit odd, to be honest. If you want to write your functions that way, go for it. There's nothing stopping you. Okay, so let's have a look now, just before we wrap up this video, at 2 more things. So you could define, well, it's not, yeah, you could technically define a function with no parameters. Say, for example, you wanted to define a function that tells you what your favorite blockchain project is, you know, in case you forgot. My fave project. Right? You didn't need, because you might forget about what it is, you're not going to give it any inputs. So you just wanted to tell you what your favorite blockchain project is, or anyone else's favorite blockchain project, right? So we're not going to take any inputs. So notice here, I have put a space before I specified the equal, but I didn't specify a label for any inputs. I just specified a label for a function, my favorite blockchain project, and I'm going to return the string Cardano. Right? And if we hit OK, so that defines it. And then if we copy and paste that, now every time I call that, it always tells me Cardano. Right? Now in the functional programming world, now that I've defined that, in a pure functional programming world, that stays the same, well, stays the same forever, sort of. Basically, you have this notion of, with functions, for a given set of inputs, you always get the same outputs, right? So we have this output defined, no inputs, right? But if there was inputs and this was the output, every single time you supplied an input, you would always get the same output. If we went back to this added to USD function, no matter how many times I call it, with 575, it should always produce the output of 46. And again, that makes it really easy to reason about the behavior of your application, and that's very important. So my favorite blockchain project will always return Cardano. And we've not really here defined a function. What we've done is defined a name, given a label to a string, basically. You might do that to store constants, i.e., information that never changes. So it's just worth bearing in mind that. So let's have a look here. I'm just looking over my notes. So what we'll do is we'll do a final function which introduces a bit of a more advanced concept if you've never dealt with this before, but it's just conditional logic. So if a condition is true, then we do something, otherwise we do something else, is basically it. So what I'm going to do is going to write an acronym buster function, and it'll try and bust some blockchain cryptocurrency acronyms that are bandied about a lot. Right, so acronym buster, and what we're going to do, so that's the label of the function, and then it's going to take an input, which is an acronym, and then we are going to bust this acronym for people, right? So acronym buster. So we're going to use some conditional logic. So if the acronym is equal to the string proof of stake, or POS as some people might know it, then, right, we're going to return the expanded acronym, so proof of stake. But what we need to do with conditional logic in Haskell is we always have to return the alternate. We always have to define what the behavior is going to be if this is not true, because this could potentially not be true. Okay, so far we're saying if acronym is equal to POS, then return proof of stake. Otherwise, defined by the else keyword, say I have never seen that before. Right, okay, so hit enter and make sure that you get no errors. That's great. And then let's use this acronym buster on proof of stake, right? And we get out proof of stake. If we do proof of work instead, it will come back and say, I've never seen that one before because I've not defined what POW actually is. But again, if you go back to proof of stake, you'll always get proof of stake. So that concludes the main basic concepts of Haskell that I wanted to go into this video. In the next video, we're going to go into lists in Haskell, one of the most used data structures in the language. It'll be really interesting, because things like strings are made up of lists, of characters, and there are just a number of interesting things that you can do with lists themselves. It's a really important concept that you need to grasp. So thank you very much for taking the time to watch this video. I hope you enjoyed it, and I hope you like it and share it with as many people as possible. Again, my name's Vincent. Take care.